Good. We are still in section 1.2 where we want to understand what kind of problems is this course about. And the first class was linear equations and we talked about that. And now we just spoke about linear least squares problems, as you should say, and how to solve them. So recall solving this here is connected to the inverse operators, whereas solving these is connected to the pseudo-inverse, the Moore-Penrose pseudo-inverse to be more precise. Let's not forget about problem 3, eigenvalue and spectral problems, but before we will do so, let me give you a little insert that gives you a completely different approach to the inverse and the Moore-Penrose pseudo-inverse. Okay, where are we? Here we are. Let me call that little insert an algebraic approach to A inverse and Moore-Penrose pseudo-inverse. What do I mean by that? Well, it's fairly straightforward for A inverse. You say that A inverse is the only b going from y to x with A times b is the identity and b times a is also the identity. Let me try to illustrate that. It's not too difficult really. Set x, set y, a goes this way, b goes that way, and if b is the inverse, then you could for example start with little x over here, then follow your operator a to the other side, which would give you b equals ax over there, but then the inverse would take you back from b to x. Right, so you would end up back at x. So you start with x, you apply a, and then you apply b, and the result is x. You could abbreviate this as, or you could first say, okay, x. I could also say it is identity applied to x. And if this is the case for all little x's, then you would just say the identity is what you get when you have b and a followed one by the other. Well, this is formula that you see up here. The other one is checked in the same style. I should add one little detail here. The identity map I'm denoting here by I is actually the identity map on the set capital X, right? So Ix is a map from capital X into capital X, and it takes little x and maps it to just itself, right? This is what this equation says. So to be precise, we should put a little capital X down here, whereas we have to put a little capital Y down here because this is playing on the other side. That's how you can understand the inverse. It is the operator that will undo what A has done. Well, not too surprising, I guess. But now here's maybe the surprise. One can define the Moore-Penrose pseudo-inverse in the very same one, pretty much same style. You would say this is the only b from y to x with, okay, and now cannot start like you did before, but because there will be no b with this property, or maybe there will be no b with that property, so you have to write down somehow weaker versions of these, and they look like this. You would say, if I take AB, I want this to be I, but maybe it doesn't quite work. If I multiply it by A again, then it should be A. And if I did the same for the other, if I took B times A, well, I'd like that to be I, but maybe it doesn't quite work. But if I multiply by B again, well, then it should be B. It's clear that if you have these properties up there, then you will have those properties down here, but not generally the other way. In fact, it's not enough to write down these two wishes, these two properties. These are not enough to pin down your operator B. There's more than one operator B which is subject to these two equations. Every operator B that you find that is subject to these two equations would be called a pseudo-inverse of A, but the Moore-Penrose pseudo-inverse is the one pseudo-inverse that also has two other properties, and they are as follows. You again look at A times B. You say, I'd like it to be the identity, but it probably wouldn't work. Well, then at least I want that the adjoint of this is AB again, and the same for the other way. So everything should be symmetric here. So B times A should be self-adjoint. So the adjoint of B times A should be B times A. Recall, for matrices, the adjoint is defined as the transpose matrix and then complex conjugated. The adjoint of an operator will be introduced in chapter 2 in a couple of weeks from now. So the interesting thing is that with these four conditions, again, you're pinning down exactly one operator B, which does the job, and that's exactly the job of A plus that we've been describing by completely different means. Remember what we said before? We said, oh, we're minimizing the error here, and then after we did that, we're minimizing the element there, and this looks like a rather, well, numeric approach maybe. Whereas here, this is a purely algebraic approach, and interestingly enough, it leads you to the same operator A plus. If I didn't say it before, then I should say it at least now. A plus is linear. So I'm not putting this as an exercise problem because it's a bit too complicated for that. We will understand it at some point in chapter 3. So I just want to say it out loud now. So it's again linear. Maybe we should say one more word about where these funny equations come from and how to make sense of them in the same style as we did above. So let's start with this green one. So suppose you start with your little x here, then you apply a to it, which brings you over here to ax, which is also what we call b, and then apply the operator b, which from here brings you back. So what is, well, in this case it's not the inverse, in this case it would be the pseudo-inverse, and that solves the equation as good as possible. Well, maybe there's more than one solution here. Then it would pick the solution that is closest to 0, maybe this one here, x tilde. So b actually brings you down to x tilde, not back to x. So you can see that this is not the identity, a followed by b. But if you apply A again, then what would you get? Well, you would apply A to x tilde again, but x tilde also solves the equation ax equals b. So applying A again to this would bring you forward to the same b where you've been in between. Okay, and that's telling you that, should we write it all up? So we have ax, that was b, then apply b, well that was x tilde, then apply a again, that would give you b, but b is just ax, so indeed ABA seems to be A. Okay, the same style you can check the other one.